Welcome back. This is it. We're here. This is the last topic, ADV Physics C. And the last topic is inductance. So inductance is a property of things called inductors, which is just a different name for solenoids and toroids. So it's a solenoid. It's an inductor. What happens in an inductor? You pretty much already know. They store energy in a magnetic field. That's important. They also, when you run a current through them, so you're creating a field that way and a flux that way, that when you run current through it, if there's no current, then you run current, that's an increasing field. So increasing field means that's a changing flux, so you're going to have an induced EMF the opposite direction. And that's the main principle that's going to kind of work into what we're going to go over with inductance. So let's get into it. This is the end of Physics C, and let's go. So an inductor is any component that stores energy in a magnetic field. Now this does make any conducting wire technically an inductor, but in order for it to be an appreciable amount of energy, it has to be many loops of wire. So loops of wires are basically what's going to be an inductor, so that's either going to be a solenoid or a toroid. Now if you only know one thing about inductors, if you only remember one thing about inductors, it's this right here. So inductors, and this is super important, they resist changes in current. So they're not resistors. Resistors resist current in general. Inductors resist changes in current. And something else that's super, super important, you can't just have current and inductor change instantaneously. It has to change slowly over time. This is looking at this little GIF here. Looks at what happens when you apply a current through an inductor. It's going to build up a magnetic field. That magnetic field is going to be with a change in flux coming with it. So that's going to create a back EMF to oppose the current trying to come through it. And that's going to stop current from jumping instantaneously in an inductor. This is a schematic of a circuit with an inductor in it. This little loop of wire right here, that's what an inductor looks like on a schematic. And let's say we connect power. So we're going to close the switch. And there's current leaving the battery. Now the current leaving the battery is going to send, obviously, current through the loops of the inductor. That's going to create a magnetic field. Now that magnetic field, because the current, remember, current cannot change instantaneously through an inductor, so it's going to be an increasing current, which is going to create a changing flux this way. That's going to create an induced EMF in the opposite direction. So that increasing current and that change in flux creates what's called a back EMF. So that's the induced EMF that goes against the battery EMF, because the battery EMF is trying to go out of the battery this way. The back EMF opposes it. That's why it's called back EMF. And that's going to make it so that current doesn't flow right away, because the back EMF opposes the battery EMF. It causes no current initially. Now, after a while, you're basically going to have the current reach a steady value. When the current is constant, then the field in the inductor is constant, and you no longer have a changing flux, so there is no EMF. Now, there's still going to be energy stored in the inductor, but it's not going to impede the circuit anymore. How inductors behave in a circuit. So I have two identical circuits here for the most part. They both have a single resistor, a battery, and a switch. The one on the left has no inductor. The one on the right has an inductor. So when I connect power to the switch on the left, the current's going to build immediately. So I have current, it's battery voltage over R, and that happens right away. There's no delay whatsoever. On the right, I have an inductor. An inductor that's going to resist change in current. It's not going to resist current like a resistor. It's going to resist the change in the current. So when I flip the switch here, the current's going to start flowing, but at a slower rate. Now it's going to increase its speed over time. And it'll eventually, because it has the same resistance as the circuit on the left, it'll eventually have the same current as the circuit on the left. But that happens slowly. So one more time. I'll disconnect those circuits. So the one on the left, current starts flowing immediately. The one on the right, there's impedance to the current, which is a resistance and change. So the current's going to start flowing slowly. So as we stall, the circuit with no inductor is going to get its steady state current, which is epsilon over R, the battery EMF over R, immediately. That should be a straight line. But it's not going to have any wait time to get to that. It's going to connect power. It's going to immediately jump to epsilon over R. The circuit with the inductor, it is going to get to that same exact steady state value, But due to the back EMF, which is going to decrease over time, it's going to build there asymptotically. Okay. And all that happens because of a property of circuits called self-inductance. Now, self-inductance is something that happens in an inductor, but it is a property of all circuits. That's why I just have a simple circuit here with no inductor, because any wire is going to have some self-inductance, because any wire is going to create a magnetic field. So the magnetic field, when you connect power, is going to have a changing flux through it, which is going to create a back EMF. So there's current coming from the battery. There's a magnetic field in the wire. And that wire will create an induced EMF, which is a back EMF, and it's equal to, by Faraday's law, negative N dphi dt. And that induced back EMF can also be given by this right here, negative L di dt. So di dt is the change in current. L is a new quantity called inductance. And inductance is similar in a way to inertia. It's not resistance. So resistance is resistance just in general to current. Inductance is a resistance to a change in current. So this equation right here is almost analogous to this. Back EMF is kind of a force that's going against the circuit, and that equals MA. So this is the change in current. This is the change in velocity for something in mechanical physics. So this is somewhat, I mean, not really, but a little bit analogous to the mass here. It's resisting a change, and that's inductance. We'll get what it is right now. So inductance is a property of inductors, obviously, and it's the ratio of how much flux they can create. So inductors create a magnetic flux, which is going to influence the amount of back EMF they can create, because back EMF is change in flux over time. So it's the amount of flux that goes through that inductor per current given to it. And that's the formula right there. So it's N, the number of loops of the inductor, times the amount of flux that's going through it per unit of current. And to derive the expression that we just saw there, I would have L equals dphi dt, which is epsilon, over di dt. And there we go. So the induced EMF is negative L di dt, and that is inductance. And there was that N in that equation, so more loops means you're going to have a better inductor. Less loops, you're going to have less flux, so not as good of a conductor with less loops. All right, the units of inductance are henries, which is a strange name for unit, but that's because it was named after an American, Joseph Henry. He actually discovered Faraday's law after Faraday, but independent of Faraday. Example A looks at how the self-induced EMF works in an inductor. So consider the solenoid shown with current flowing in the direction indicated, so from right to left. Calculate the direction of the induced EMF when current is increasing. So this is going back to Lenz's law here. So something that's true always in physics, when something is increasing, the change in that thing is in the same direction. So the current, and thus the field, and thus the flux, is to the left and increasing. That makes the change in flux dphi dt also to the left. And then the induced EMF is going to try to oppose the change in flux. So the self-induced current, the self-induced EMF is going to go to the right to oppose the change in flux. And part B is just the opposite answer. So the flux again is to the left, but now it's decreasing. So the change in flux is to the right. So the induced EMF is going to tend to push to the left. This is what makes inductors pretty useful in a circuit. If the current were to cut off, what the inductor is going to do, it's going to resist the change in current. So rather than the current cutting off immediately, it's going to happen slowly. So it'll actually keep pushing the current along a little bit for a finite time, because an inductor can only store a finite amount of energy.
Example B, calculate the self-inductance of a solenoid with radius of r. That's the radius of each loop. A length of L and N loops. So self-inductance is number of loops, flux over I. And then the flux is magnetic field times area through the solenoid over I. So that magnetic field, this is the magnetic field of a solenoid, which we derived with Ampere's law. And using Ampere's law, the magnetic field of a solenoid was mu sub 0, number of loops, current through the solenoid over L. The area of each loop, obviously it's a circle, pi r squared, all over I. And then the current cancels. Now the current has to cancel because inductance is a property of the actual solenoid or toroid of the inductor. And that's any circuit you put it in, it's going to have the same inductance. So the inductance is not based on current. So our final answer for the inductance is going to be n squared mu sub 0 pi r squared over, and it's not capital, I had a capital here. It's lowercase l because capital L is taken for inductance. And that's the final answer. Now this will be true for any solenoid, but you should be able to derive this expression. So when you run current through an inductor, a magnetic field is going to build in the inductor, and that magnetic field stores energy. So the B field here is going to store energy. And we can find that energy using work. So it takes work to give that energy, and then work is going to be equal to the integral of power dt, because power is the rate at which work is being done. And then in a circuit, power is voltage, so EMF, times current. And when you have an inductor, the EMF in an inductor is L di dt. And we have the dt's cancel. So the work here is going to be equal to the integral of Li di dt, which gives you that the energy stored, which is equal to the work, so this is the work, which is the energy stored in the inductor, is 1/2 Li squared. Right, so that's the equation for the energy stored in an inductor. Example C. A toroid with n turns has a radius of r. That's the radius of each loop, not the radius of the toroid. And a cross-sectional area of A. A current of I flows through the toroid. What is the energy stored in the toroid? Okay, so energy is 1/2 Li squared. So I is given to us, so let's go ahead and find L. So L is noi, n phi over I. And then phi is BA, the magnetic field times the area of the toroid. And then the field through a toroid, again, we found this with Ampere's law, so I'm not going to drive it again here, but it's mu sub 0 n I over 2 pi r. And again, inductance is not based on I, so that's going to cancel out. So the inductance of the toroid is mu sub 0 n squared A over 2 pi r. And then to go ahead and just find the final answer here, U is 1/2 L, so L is all this stuff, for 2 pi r, times I squared. And you get what you get. It's not a pretty answer, but that's the answer here. It's mu sub 0 n squared A I squared over 4 pi r. And that's the value of the energy stored U. And that's it for inductance. In the next one, we're going to look at inductors and circuits.